Well, hey, everybody. Welcome to the Weekly Space Hangout for Friday, September the 11th, 2015, our return from the summer hiatus. I'm Fraser Cain, publisher of Universe Today, and this week we have arrayed an enormous group of guests to talk about a topic that's very special to all of your hearts. So I'm going to introduce some of the special guests first, and then I think you'll probably get a sense of what this conversation is going to be about. So joining us this week on the Weekly Space Hangout, we have got Alan Stern from Southwest Research Institute, and of course, the Pluto New Horizons mission. Alan, welcome back to the Weekly Space Hangout.
Thanks, Fraser. Excited to be here.
I can't wait to pick your brain. We've got Alice Bowman, who is also works on the New Horizons mission. I would say it's the mom, but it's the missions operations manager of New Horizons, which is awesome. So welcome for the first time to the Weekly Space Hangout, Alice. We really appreciate it.
Yeah, nice to be here, Fraser.
And we've got another sort of sometimes regular, sometimes special guest. I've decided she's now shifted into special guest mode, and that's Emily Lakdawalla from the Planetary Society. Emily.
Oh, great to be here.
And a regular cast and crew. We've got Brian Koberlein. Brian.
Hi.
We've got Dave Dickinson.
Hey, still in Florida, still writing.
Awesome. We've got Morgan Rehnberg. Hey, Morgan.
Hey, Fraser.
And we've got Ramin Skibba. Hey, Ramin, how's it going?
Hey, pretty good. Glad to be back.
All right, so we are going to spend a vast portion of today's episode talking about Pluto New Horizons, of course. Not only did the mission happen during our hiatus, but there's been a ton of new images and information and data that's been released literally just in the last couple of days, so our timing couldn't be better. If we run through all of that and exhaust this conversation, then we've got, in addition to that, some other crazy topics like Elon Musk's plans to nuke Mars, the discovery of neutrinos from the cosmic breakaway background. We've got some really interesting topics as well on top of that. So an upcoming eclipse, so it's going to be a pretty good show. Apparently a lot of space stuff has sort of been collected for us, and now we're ready to deal with it. So as always, this is an interactive experience. You can absolutely communicate with us here on the show. There's a bunch of ways that you can do that. One is that you can use the Q&A app, and if you are watching the show and it says that we're interacting live with the audience, all you have to do is click, and then you'll still watch the video, but now you have a chance to post a question. And I'm going to say hi to Jim Meeker and Guido Bibra and Nancy Graziano and Lionel Ward and Andrew Planet and David Dunn and Bert Walters and Michael Meyer and Sev Dustbunny and Gazelle Sabarin and Gennady Romanov Cherengovsky and Elad Avron and Tom Van Scotter and Matt Woods and Sylvan Westby and it just goes on and on and on. To everybody, all of the Weekly Space Hangout crew. Sorry I didn't get to all of your names. There's a lot of people saying hi. I know you're all really excited to have this back and happening, and so am I. So let us begin with the big topic at hand, which is, of course, Pluto New Horizons. So as I mentioned just before the show, asking Alan, did you do anything interesting with your summer?
Well, I guess that's up to you to decide. I had about the most interesting summer I think I've ever had. It was fabulous. So
I'm not even going to say if you've been living under a rock. Obviously, we saw the close-up pictures of Pluto thanks to New Horizons. So, Alan, can you give us the update on what's happened since the flyby back in July?
Well, there are a number of things that have happened since the flyby events, and Alice can speak to some of it on the mission operations side. As a science team, we've already been digging into the data that came down in July and making some discoveries. We've already submitted a paper to Science, to the journal Science, with about 152 authors, I think, at last count. And it's in the review process. We've also started to make plans for a whole sweep of papers to be submitted next month in October. We made plans to give talks at the Division of Planetary Sciences meeting in November. There'll be almost 80 Pluto and New Horizons talks at that meeting in Washington, D.C. Pretty technical talks. We've been planning for the extended mission, which we'll propose to NASA next year, and we've been working to plan the downlink that's going to take over a year to get all the data to the ground. So we've been pretty busy.
And that's, I think, one of the things that a lot of people don't realize is that there's so much data was gathered at this moment, and now in the moment of the flyby, and now we're waiting for all that data to percolate back to Earth. So how much of the total data have you received so far, and what is still what future Christmas presents are you expecting?
Yeah, you might remember we flew by Pluto and made closest approach on the 14th of July this year, 2015, and that happened to be the 50th anniversary to the very day of the first flyby of Mars by Mariner 4 in 1965. And I mention that because we actually looked up how much data they sent to the ground after their first flyby and compared it to New Horizons. New Horizons is going to send about 50 gigabits of science data to the ground. That's not any engineering data. That engineering data is on top. But the Pluto science data set, meaning the Pluto system science data set, is about 50 gigs. And that's several thousand times the amount of data that Mariner 4 sent back from its first flyby of Mars. Now, you asked how much data is on the ground. Depends on which instrument. For example, for our two plasma instruments, SWAP and PEPSI, all their data from the flyby is on the ground now. They're pretty small data sets, and Alice's team, working with our science operations team, sent that back in August. Student dust counters data is also all on the ground. But then take the Alice UV spectrometer, a little bit less than 3% of its data is on the ground, and the other imaging instruments are similar. So the average across the entire payload is that we've sent about 5%, maybe 6% of the data to the ground, and it's going to take about another year to send it all back.
All right, so Alice, you've been described as the mom of the mock. Is that right? Can you, for people who aren't familiar with what you do, can you explain your role in the mission?
Sure. MOM stands for Mission Operations Manager, and I lead the team that's in charge of commanding, operating, and making sure that the spacecraft is healthy and safe on its journey and through the flyby. So that's, in a nutshell, what we do. We take care of any kind of problems that are we experience on the ground. That could be the communication link between our ops center here and the Deep Space Network, that whatever antenna we're using, or it could be any problems on the spacecraft. So we're the first line of defense.
And how is the spacecraft doing?
Spacecraft is doing very well. It's healthy. We're getting back gobs of data. As Alan can attest to, this weekend there was a flurry of emails going back and forth amongst scientists, just oohing and eyeing over that data. And you saw some of that posted on the website, yesterday evening. So we've been focused on getting that data down. We've updated the ephemeris on board the spacecraft so that it knows where it is. And we've been negotiating tracks with other missions that use the DSN, and keeping that spacecraft healthy.
It's fantastic. So both Emily and Morgan are sharing here images of this recent data set. So Emily has the one, I guess, with Pluto and Charon and the two smaller moons, Nix and Hydra, and then Morgan's got this one of the closer up images of Pluto. So let's pick one of these, Alan. Let's start with this the close-up one that Morgan is showing right now. I'm highlighting it here, that shows Pluto in higher resolution. What's new? What should people be thinking about as they look at this picture?
Is that the one in black and white?
Yeah.
Chromatic, yeah.
Yeah.
Yeah, well, that's a very nice synthetic global view in which we stitched together a mosaic and wrapped it on a sphere of the size of Pluto, and then projected the view as if we were suspended about 1,000 miles above the planet, looking back. And it just gives you, I think, a breathtaking view of how diverse the geology is, and also how diverse the seasonal volatile transport must be on Pluto's surface. That actually consists of more than a dozen frames made by the LORRI camera, which is 1,000 by 1,000 silicon CCD. No filters, just maps panchromatically across the visible, which is normal for a silicon chip. Each of those is about 400 meters per pixel, So each individual frame is about 400 kilometers across, about the size of western Colorado. And we stitched all 15 of those together along with some lower res out towards the margin, just to give sort of a planetary view looking down on Pluto. And I think it's magical. It's absolutely breathtaking.
And you could see those mountains made of ice there. I mean, just the really strange processes that are happening on the surface of Pluto. It's just stunning.
There's a lot going on there. Obviously, you know, the big central area that you see that's so bright is the left side of the feature people call the heart on Pluto. We informally call this Sputnik Planum, after Sputnik, the first space explorer, robotic space explorer. Surrounding the planum itself, or plane, is about the size of the state of Texas. So you're looking at a very large region there geographically. Surrounding the plane on many of its borders, you'll see mountain ranges. And there's some pretty steep mountains and some pretty tall mountains, in fact, about as high as the Rockies here in Colorado. So we know that by just doing the trigonometry and looking at shadows. Later, we'll actually have the same views from other angles, which will allow us to build a digital elevation map from stereo height recovery techniques. But we can already pick out individual places and do the height reconstruction one by one. And those mountain ranges are pretty impressive. They can't be made of the same stuff as the planum, because we know that it's made of nitrogen, and nitrogen is too soft a material to build mountains out of, even in Pluto's weak gravity. So it must be something stronger. The two most likely things are rock and water ice. But it's most likely water ice because the rocks almost certainly sunk to the center of Pluto. The planet's probably differentiated. The water ice is the lighter stuff, so it would float to the top and form the mantle and perhaps the crust of Pluto. So we think that the volatiles like the nitrogen and methane and carbon monoxide that we see there, the stuff that shifts around with the seasons and interacts with the atmosphere, is a veneer or a coating on the surface. Some places it may be very thin, and even looks like there are places where it's breaking up, it's so thin on the margins. But there are other places where it may be quite thick, even kilometers thick. And we'll just have to see when we have more data.
All right, and now Emily has highlighted a different photo here, so I'm going to switch over this. And why don't you go ahead and let us know what we're looking at in this picture. It looks like one of the moons.
Oh, for me, for Alan.
Yeah, Alan. Emily is just showing pictures that she finds interesting, literally just picking up pictures going, what's this? And
so Fraser, that is Pluto's small moon Nix. Actually, Pluto has 3 classes of moons from a size standpoint. Its big moon, Charon, that was discovered in 1978, is about half the size of Pluto. It's about 1,200 kilometers in diameter. And then beyond Charon, which is the innermost moon, are 4 small moons. 2 that are intermediate in size. This is one of them, Nix. It's actually perhaps 40 or 50 kilometers across, and you can see it's irregularly shaped, as you might expect for an object that small. And then further out are the others. This one's Nix. It's relatively close in its orbit to Charon. And this is an image that's actually a composite of our best available Lori panchromatic image with color from the Ralph instrument draped on top. And the most prominent things about the image, I think, are first that we can measure the size and the axial ratio of the object. We can also determine its reflectivity, and it's pretty high, as we've said before. It's pushing 50% reflectivity, which is brighter than the ices on Charon and rivaling some of the places on Pluto. That's a puzzle. And then, in addition, you can see right smack in the middle of the object is what looks like a crater. And that crater has surrounding it some red material that may have been excavated from that hole in the ground. Whether that's actually an impact crater or something else, a little bit TBD. And you know, it's interesting that we don't see a lot of other craters on this surface. And we have some ideas about that, but it's still early days.
It's kind of interesting, Ellen, I think, that we didn't discover any new moons on this flyby.
David, I completely agree with you. we were shocked. I don't think anybody on the science team expected that we would find 0 new moons. We had actually had a betting pool, and some people had bet we'd only find 1 or 2. Some people bet that we could find as many as dozens. But the history over the last decade, from 2005, when Nixon Hydra were discovered, and then we looked harder, in 2011, we found Kerberos, and then we found another in 2012, and the science team really was expecting to find more moons. We didn't, and that is a bit of a mystery.
All right, I'm going to switch over to Morgan's view, and I think this is Sharon.
Yeah, this is a color composite made the same way of Sharon. Again, you see a big spherical object here because it's large enough to shape itself by gravity into a sphere, like all small planets and big planets do. Now, Sharon is covered in water ice. It doesn't have any of the volatiles that Pluto's surface does, and you can see it's a very different appearance from Pluto. A lot of people say it looks to them to be more dead. But if you look more closely, you see a lot more than just craters there. Up at the top, there's that big dark stain over the North Pole. We have some ideas about that, but it is early days. We'd be very interested to know, and we may be able to determine later from other imagery what's going on at the other pole, which is actually in permanent winter shadow right now, and we could only photograph looking back after the flyby. And that's a very tough data analysis problem because of the glare of the sun. In addition, though, you can see that there are faults or other kinds of tectonic features on the surface, big canyons, clear evidence that there was some evolution on the surface, not just things bombarding it from the outside, but Sharon has its own history. It doesn't have as diverse a geology as Pluto by any extent, or as diverse set of reflectivities and colors as Pluto, and to our knowledge, it doesn't have an atmosphere either, which Pluto does. But we actually have a data set that's going to be coming to the ground in the next few weeks, in which we can probe whether Sharon has a very tenuous atmosphere. That's from our Alice ultraviolet spectrometer, and I'm really itching to get my hands on that data set because there are a whole lot of us that have done modeling of how Pluto's atmosphere escapes, and in many of those models we find that some of it temporarily accretes onto Sharon, and so Sharon could have a secondary atmosphere, and the Alice spectrometer will tell us the answer once we get those data to the ground.
Alan, are we going to see any better views of this groove sort of on the edge of Sharon here?
We'll have better views of the entirety of Sharon. These that you're looking at now are a few kilometers per pixel, and we will have a global map in the end that's at several times better resolution, better than a kilometer per pixel, but those aren't on the ground yet. The difference in this image and what we had in July is that this set of data was transmitted with lossy compression, so it could be rapidly downlinked back in July, and now we're sending it at a slower pace, but without any of those artificial JPEG compression artifacts marring the data.
So it's like one of those when you browse the web, and the image gets better and better as the data sort of fills in.
That's right.
Emily, I know you've got a question as well.
Yeah, I've got a screen up now here showing the raw image website from New Horizons, and actually before I ask my question, I just want to thank Ellen for sharing all of the raw data on the internet within 10 days of its acquisition. That's pretty awesome, and it's going to make every Friday afternoon kind of busy for me. I'm wondering, I know that the plan has changed from the original plan, just downlinking the JPEG compressed data first before going to the uncompressed stuff, and I'm wondering what changed about how did the spacecraft behave differently, or from what you predicted? How did the data look differently from what you predicted that made you make that change in decision? I don't know if this is a question for Alice or Alan.
Well, I can take it. And first, I'll say thank you. I'll accept your thanks, but the thanks for putting that data on the NORI website really goes to the entire team, not to just Alan. When we planned the mission back in 2001, we plan to send the data to the ground in this more rapid-fire manner by compressing all the images so that we could get about an order of magnitude less data, everything in a browse data set, and then get that to the ground over just a period of a couple of months. And the idea was, after the Pluto flyby, you wanted to get everything to the ground as quickly as possible, even if it had some compression artifacts, just in case the spacecraft were to go bad on you later. But what we found when we actually started sending the data to the ground is that we were always squinting at it to try and learn the most about the smallest features and the most, the smallest details that were most informative about the geology, the volatile transport, also the same in the spectra. And we were getting pretty frustrated with the JPEG artifacts. So it became obvious that that was actually the wrong way to go. We had a very healthy spacecraft. We had most important data called Group 1, all stored redundantly on 2 different solid-state recorders on New Horizons, and that by sending home the noisy, lossy compressed data, we were actually delaying getting the good stuff that we could really dig in scientifically. In some ways, we were actually increasing the risk because you had to trade the risk of very tiny risk of losing New Horizons suddenly 9.5 years into flight when it's been so healthy all the way along, against the risk of not being able to work with the real lossless, the very best data. And scientifically, that was just an upside-down trade. So we went to NASA headquarters and talked to them about this, and they said, you're right. We think you ought to begin the lossless compression as soon as you can. And so then working with Alice's team, we managed to get that going here in September. And that's the way we're going to proceed from here on out. And in the end, one bonus, Emily, is that because we don't spend another couple of months doing loss E compression, we will actually finish the entire download a couple of months early. And so you can see where there are benefits in terms of risk as well, and benefits in terms of everybody's just anxiousness to get the data to the ground and be able to see all that's there.
Alice, I have a question for you. I'm wondering if, this mission, it's such a kind of throwback mission in a way because it's one of these first flybys where everything has to work the very first time. Not, and everything seems to have gone really, really, really well, but not everything can have been exactly as you planned. So were there surprises about, I'm not asking about bad things that happened, just things that you didn't expect or predict, or you're like, oh, that's funny, something odd about the flyby, anything that happened in July?
Other than July
Perhaps
4th.
Other than July 4th.
Yeah, that was unexpected. Something we didn't want to experience, but we were prepared for it. We had, good contingency plans in place and a great team, and everybody responded, so everything worked out just fine. In terms of more subtle surprises, which I think is what you're asking, you plan for all these contingencies, and they sound somewhat far-fetched when you're doing the planning of them. We had this planned, if our primary mission operations center went down for some reason, and if it was whatever caused it was some catastrophic failure somewhere over on the East Coast, and all the planes were down, sort of like, 9/11, we would get in a van. We had 2 drivers on standby. We'd get in a van and we'd start driving to JPL, where we had a remote mission operations center ready to go if in the event that happened. Thank goodness that didn't happen. We had all these plans to do these knowledge updates if for some reason we found that we weren't going to hit that aim point if we were outside of those boxes that we needed to hit. The team was prepared and we did all that work, but thank goodness we stayed within those boxes. So I guess, at the moment, nothing is really coming to mind that we didn't anticipate, except for the July 4th anomaly. that we had. And that was due to an overload. We sent too many instructions to the main computer, and it pretty much decided it needed to reboot, and that's what it did.
What was it like having that experience? Maybe you can give us a little bit more of an insight of sort of your adventure through that sequence of events on July 4th.
Oh my goodness. That was probably an adventure that I don't want to repeat. July 3rd, we loaded the flyby commands to the backup computer because the idea was to have both computers on just in case one failed, and that we could pick up with the flyby sequence using the other computer. So we put those commands up to the backup computer on July 3rd. We couldn't put them up on the main computer until the short set of commands had finished executing out of the memory area that we were going to use. So that first opportunity opened up on July 4th. These sets of commands that we sent up to accomplish the 9-day flyby took a little less than 2 hours to radiate to the spacecraft. And of course, we had to wait a round-trip light time, which on July 4th was a little less than 9 hours, to see if those commands were going to be accepted by the main computer. And we had practiced this on the ground. We practiced this on the spacecraft. But there's nothing like the real deal, right? So we started radiating these commands at about 4:30 in the morning on July 4th. And about a little bit after 1 p.m. Eastern local, we were watching those commands get into the main computer, be accepted by the main computer. And we were about 40 or 50 minutes in to watching these commands get in when we lost communication with the spacecraft. Total silence. What a terrible feeling. Checked our ground system because many times the problem is in the ground, not on the spacecraft. Spacecraft would be fine. But in this case, the ground system was perfect, nothing wrong. So, we've had a few anomalies over our cruise to Pluto system, and we all knew what we needed to do. We weren't sure what was going on, but the first order of business was try to establish communication link again with the spacecraft. And I asked the autonomy engineer, okay, give me the most plausible faults, because I didn't want to spend time on anything that wasn't the big thing that could have happened. He came up with 2. One of the 2 scenarios we had seen before, and the response of the autonomy subsystem would take about a little less than 110 minutes to reconfigure the spacecraft and start putting this signal out to Earth. The other anomaly or fault condition was something that we'd never seen on the spacecraft and really hoped that we would never see on the spacecraft. But that fault path would have a reconfiguration of about 50 minutes. So I looked at the wall clock, and we were about 65 minutes or so into having no comm with the spacecraft. And so I said, okay, let's go ahead and reconfigure the ground station. We were actually up with Canberra Station at that time. Reconfigure that and see if we can lock up to the signal that would be output in the event that we had a switch over to the backup computer. And we locked up to that spacecraft about 77 minutes after we lost comm, and it was a wonderful feeling because we knew that if we got that signal from the spacecraft, we had 100% chance of addressing the problem. The question then was, did we have enough time? Because this was July 4th. The flyby sequence was supposed to start on July 7th. Our round-trip light time is a little less than 9 hours. So that took up all of our time for the next 3 days. And the end result was that we did engage that flyby sequence at 12:24 p.m. local Eastern time, right on time, and had a great encounter.
Go ahead, Emily. I know you've got a question.
Yeah. So this is for Alan. One of the very first science results you were able to talk about after the flyby was the radio occultation, and that told you that how thick Pluto's atmosphere was. And the answer that your spacecraft is getting is really different from the answers that we're getting when we look at it on Earth. And I'm wondering, it's one of the most common questions I'm getting from readers. How are they going to reconcile?
Yeah, that's a great question. And in fact, a number of things that we're seeing in Pluto's atmosphere from location on Pluto is very different from what people have seen from the ground. You might know that there was a stellar occultation from the ground that was very well observed on June 30th. And some of those observations were specifically designed to look for hazes and discovered no evidence of hazes, but we have clear and unambiguous proof of the hazes in the images like the ones that were released yesterday and also back in July that show that glow around Pluto's hard deck, which is the clear indication of atmospheric hazes, and we see haze layers and more structure in the hazes, and yet from the ground, no evidence of it whatsoever. So, you know, that's the power of exploration, is actually being there. Now, our radio occultation results are indicating that the surface pressure, this is what you're referring to, at the base of Pluto's atmosphere is about 10 microbars. Most of the ground-based results are giving numbers that are somewhat higher, in the range of 15 or 20 microbars. So a factor of 50% or 2 times as high. But it's not clear to us, and I don't think it's clear to anyone, including the ground-based observers, why this difference. It may be that something about the ground-based technique just doesn't correctly extrapolate to the surface, because they can't see to the surface. They can only see to an altitude about 50 or 100 kilometers, depending upon the experiment, above the surface, and they have to mathematically extrapolate down. We actually see directly to the surface. Now, it could also be a number of other things, and our results could be wrong, but we've got a very clean signal at extremely high signal-to-noise, and a very experienced radio science team, and a very good calibration on the instrument. So I'm putting my bets on 10 microbars, and you know, it could be as simple as Pluto is changing over time, and that just very recently the atmospheric pressure has started to decline. We'll see, but you know, that's part of what happens, I think, in every first exploration mission, is you end up colliding with some of the things you thought you knew from the ground before, and that's how the scientific process works.
If it turns out that we don't quite understand what to do with the data we get from Earth in order to retrieve the correct density of the atmosphere close to the ground on Pluto, are there any other scientific results that knowledge would disqualify, that would force you to reconsider?
I'm not sure exactly what you're asking, but I can say the data set that you're showing is a very primitive version of the real data set. It's an engineering telemetry channel from the ultraviolet spectrometer that shows how many counts it got as a function of time, and you can see it declining first gently and then more steeply due to the extinction of light due to Pluto's atmosphere. The actual data set behind that are a set of spectra made at very high cadence, many times per second, over that whole time period. And that data is still on the spacecraft and hasn't been sent to the ground. That data contains a lot more information than just the count rates that we have. And in addition, we also have a stellar occultation, which is a second kind of check on the ultraviolet results. Similarly, for the radio occultation data, we currently only have a few percent of it. We have one channel of 2, and we only have the signal as received very close to the ground on Pluto. And so we don't have the entire altitude structure. We don't have both polarizations. There's a lot more to come to the ground. We're going to be able to do lots of cross-checks between the UV result and the radio result, and I'm sure that we'll be able to build a strong case for a consensus model atmosphere as a result. I hope that answered your question, but I'm not sure if you were asking more.
That's okay. That was close enough. But it does. Your answer makes me ask, how on earth do you prioritize the data that you're sending down? I know you in particular. You're the Alice guy, so you're probably really itchy to get your hands on that. And I'm kind of surprised it's not down yet, since you're the PI.
Well, it's true that I'm PI of Alice and Ralph, both those instruments, but we don't do it that way. We actually do it a very different way. We prioritize the data with NASA into 3 different priority sets called Group 1, 2, and 3. Group 1 is the most important. And what we do is we send all the Group 1 data home before we send any Group 2 data home. There's actually a waiver process where if we've got some discovery and some data where we want to pull some Group 2 data ahead, we can make exceptions, but that's rare. So we send Group 1 before Group 2 before Group 3, and then the people who have the big votes in this are not the instrument PIs like myself, but our science theme team leads, like Randy Gladstone for the atmosphere and Jeff Moore for geology, geophysics, and imaging team, Will Grundy for composition, and Fran Bagenal for plasmas and particles. And they take turns. We send one geology, geophysics data set, Group 1 home, and then one atmospheres, and then one composition, and then one plasma, and then we start again until all of them are finished with Group 1, and then we move on to Group 2. And although as PI I get veto power, I very, very rarely use it. They're domain experts, and they choose the order within the Group 1 and Group 2 that we're going to send them to the ground, and they do it with their teams acting as kind of a committee to reach consensus.
And at this point, I'm sure they all have so much data that they have research papers to work on that are going to keep them busy for decades. So we've got a pile of questions that are starting to have come in from the viewers, and I thought I would take a quick chance and start to go through some of these questions. So this question comes from Tariq Karbaresh. Question to Alice: You've guided New Horizons all the way to Pluto. Do you think we could send an orbiter there, and is it even worth it? Thanks.
Oh gosh, that's an easy one. Yes, we can, and should we? Definitely.
How much longer would a mission take if you had to send it on a trajectory that it could get into orbit? How much longer would that kind of a mission take?
Oh gosh, I'm not sure of that. I'm not a mission designer. We did fly by very fast on Pluto. Alan, do you have any? Have you looked at that?
Yeah, I have seen studies for different kinds of orbiters, and they range in terms of flight time from very slow, that could take 20 years or more to reach Pluto, to some more innovative concepts with current technology that could actually get there in about the amount of time that New Horizons flew there, and in another fast transfer across the solar system.
Okay, great. You should do it. So if you needed any extra encouragement, I think we all agree that should happen. Oh, hey, Nicole Gugliucci has joined us.
I have a follow-up to that one, though. Is there another? Would it be better to go to a different Kuiper Belt object to get a sense of the diversity, or do you already know that Pluto is such a diverse and unique system that that's where you would want to send a follow-up mission?
We should do both. We should explore the diversity of small planets in the Kuiper Belt, and at the same time, I think we're going to want to follow up Pluto. Now, of course, resources are limited, and there's a lot of competition across the solar system. I think either one of those would be a very big step forward as a next step following the exploration of Pluto. But having both would just be icing and cake too. And as long as we're just talking here on the show and we don't have a budget, then why not go for all of it?
Yeah.
I can tell you this, Emily. I think that we're seeing, from the complexity of what we're already seeing in the Pluto system, particularly on Pluto, and people are already saying, I wish I had this kind of data set and that kind of data set to puzzle out what's really going on. For example, subsurface with radar. We don't have any kind of radar instrument on board. Could really yield a lot. More thermal mapping could yield a lot. And I could go on down the list, and being there for a long time, seeing the other side of the planet where there are clearly terrains that are analogous to ones we're seeing where we only have one example, we wish we had more, are already making people wish that we had a second flyby or another another mission as an orbiter. And I think that as the scientific community gets its hands around the data sets as they come down, that there'll be a groundswell of interest in that. And I know it'll be a part of the discussions in the next decadal survey.
And you will then blow the dust off the plans that you already have developed and say, I'm glad you asked. Let's go. So this question comes from Lionel Ward. Is it likely that New Horizons could pass within an observable distance of a smaller Kuiper Belt object that maybe Hubble couldn't see? Is it on the lookout for any such objects as it's going?
Yeah. The odds of that, calculated from mathematical models, are small, but they're not zero. However, it's very hard for us to look from the vantage point of the spacecraft, and it's really not for the reasons that a lot of people think. The LORRI camera on board is capable of detecting small KBOs that would be near our path as a few weeks in advance of a close flyby. So if it was always looking, it could spot them, but we don't have the fuel to be always in pointed 3-axis high-resolution mode for years. We would actually burn out our fuel supply long before we get to the KBO we already plan to propose for and fly to. Also, we have pretty slow data rates because the spacecraft is, after all, 3 billion miles away and working with a 15-watt transmitter. So we also couldn't send that many images to the ground continuously. And so from a practical standpoint, it's just not possible for us to be on the lookout all the time. Fortunately, I don't think we're missing much because the odds of having one that Hubble didn't discover that we might with LORRI have been estimated to be not zero, but close to zero. So I don't think we're missing much in not being our own century. And we have a very good Kuiper Belt object we're already headed towards, or not headed towards, but that we'll be burning the engines to head towards beginning next month. And in addition, we expect to observe somewhere between 15 and 30 other KBOs from a distance as we fly on our way to the close flyby. And we're going to have a lot of Kuiper Belt object data by the time we finish that extended mission if it's approved.
David, on that, I know you've got a question.
Yeah, that 2019 KBO flyby, Alan, I was curious, how close is that going to be? Do we know?
Well, it depends on what you're referring to. The flyby takes place about 1 billion miles beyond Pluto, so we have to fly that much farther. It'll be about 44 astronomical units from the Sun at the time of the flyby. If you're asking how close we can get to the KBO, we're actually conducting a study right now to look at that, and we won't have the results until later in the year because obviously our engineering team, our mission design team, is pretty busy with Pluto flyby. We didn't want to distract them with these kinds of things until we finished. But we're looking at whether we can come substantially closer than we went to Pluto. And I'll get back to you with the answer when we have it. It won't be a secret, and I guarantee it'll be a part of our proposal to NASA. The science team wants to go as close as we can without going so close that we smear images. But there are other factors, like how closely we can navigate to the object and how closely we can drive to it, that also factor in. And that's all a part of the mix in this study.
Okay.
Right, so as close as you can.
Yeah, because it's tiny.
As close as we practically can.
Yeah, and still get good data.
But you know, just like Pluto, we could have gone closer. But there were good scientific reasons to go the distance that we did, because some instruments would have lost a lot by going closer, believe it or not. Others would have gained, and we reached a consensus happy medium. I'm sure we'll do the same for the KBO, but because it's smaller, at the same distance you don't put as many pixels on it. You have the same resolution, but not as many pixels on the target. So there's a real interest in seeing if we can't go, for example, twice as close. And I just don't know the answer yet. No one does. But we'll know by the end of the year.
You only have so many shots at this over the next few decades to keep trying flybys of other objects. So this question comes from Nancy Graziano, who also sort of acts as one of the main producers of the show. So one, thank you, Nancy, for all of your work in helping getting this organized. We wouldn't all sort of be here in this fashion if it wasn't for you. So thank you, Nancy. But question, when New Horizons, this is for Alice, when New Horizons first launched and you look forward to today, did you expect the craft to perform as well as it did throughout its entire lifetime, or did you think there would be more problems than there actually were?
Well, for me, I'm a pretty positive person, and so and maybe you could say naive. I expected it to, perform as it did. So I think, yeah, it was a great cruise out to Pluto. It was a great gravity assist that we had at Jupiter. There were wonderful movies and pictures taken of the Jupiter system. It's been a good ride. Some people thought we'd get bored on this long cruise to Pluto, but I can tell you that with a small team and starting this flyby sequence as early as we did, we were not bored. And then with the advent of all those other moons that we kept discovering, or Hubble discovered, help of Hubble, it's been quite an adventure. We haven't been bored at all.
You did have a truck ready to go to drive across, directly across from the East Coast to JPL, should the need arise. So.
Yes, we did.
Awesome. Okay, Emily, you got another question.
Yeah, I was looking at the Kuiper Belt Extended Mission target, and there was a moment at which it suddenly boggled my mind just how much farther away it is than Pluto. It's almost another 50% farther from the Sun, and I'm wondering if you can talk about what that means in terms of anything you have to do with the spacecraft in order to make it work once you get to that incredible distance away.
Sure, that's a really good question. I want to preface that by saying when we competed to win the Pluto Kuiper Belt mission, the announcement of opportunity that NASA put out required all of the proposing teams to design and propose a spacecraft capable of not just Pluto flyby, but Kuiper Belt object flybys out to 50 astronomical units. So from a telecommunications standpoint, a power standpoint, fuel, instrument sensitivity and lower lighting levels, and everything else, we designed New Horizons for going all the way out, not just to 44 AU, but to 50 AU and doing flybys. So the bird is built to do this, and it was tested to make sure it met all of its specifications. And as Alice has told you, it's very healthy. So from our standpoint, there are small differences that we'll have to deal with, but no really big ones. The exposure times of 100 milliseconds and 150 milliseconds for LORRI images will get lengthened a little bit to compensate for lower light levels. The scan rates on the Ralph scanning TDI detectors will be slower so we can soak up more light per pixel to compensate for the lower light levels. I think the main difference on the spacecraft at the flyby, and Alice, you can add to this or correct me if I'm wrong, is going to be that every year we produce about 3.3 less watts from the RTG. And so when you go out to the beginning of 2019, instead of doing the flyby on a power budget of about 202 watts, we'll be operating right around 190. So in order to use all the scientific instruments just as robustly, we'll have to think of other power savings on the spacecraft to compensate. Alice, you want to add to that?
I'm having a little trouble with the sound over here, so sorry about that. Yes, we'll have a round-trip light time of about 12 hours when we get to that KBO, either December 31st, 2018 or January 1st, 2019. And our turnaround time for those, when we can get those optical navigation measurements to the ground and process that data and then turn it around and uplink it to the spacecraft to affect the trajectory time, the observation timing for the Kuiper Belt will be pretty tight. We won't have as much time as, say, we did for the Pluto flyby. And Alan spoke about the power. We think we'll have plenty of power to have what we need on, but we could be doing more switching between instruments, and perhaps we might not be able to have all of the plasma instruments on at the same time like we did during the Pluto flyby, so we might have to make some trades there.
All right, awesome. I've got a question, and I lost the person who asked it, but the question is, are there any plans to do oh, here we go. It comes from Mike Roslick. Any plans to do a pale blue dot of Earth now that maybe you've got a little time to kill between this and your next target?
Yeah, we would like to do that very much, but the Earth is seen from New Horizons is very close to the sun all the time, and that actually presents a hazard to our cameras. The engineers and instrument scientists think we can do that, but there's some risk to it as well. So we will probably do that after we do the Kuiper Belt object flyby, so we don't put any of the instruments at risk before that flyby. But I think that would be a great finale.
Yeah.
If we don't have a second Kuiper Belt object to fly by, then instruments like Glory, they've got all their science that they're going to get in terms of flyby science, and that would be the right time to do it.
That would be great.
Let's add, though, that we're doing look-back images of Pluto for scientific purposes. So we'll be looking at Pluto as a dot in the distance this fall, and then again next spring, and probably again next July for a last time.
You can't just pull it out and it won't do it.
Right. I think Alice is having some technical problems here. Ramin, I know you've got a question.
Yeah, this is a question for either of you, and Emily probably has thoughts about this too. I was just wondering, based on the data that you have so far, or do you have ideas of based on data you're going to get soon? What have you learned so far about the origin of Charon and about how old it is? I mean, is still the leading idea that it came from, that it has an impact origin, or is it possible that it was gravitationally captured, or what? I don't really know about what its situation is.
Well, thanks, Ramin. That's another good question. There's a very strong case that the Pluto-Charon system, the system of satellites around Pluto, was born in a single giant impact. And there are quite a number of clues that lead us to the same conclusion. For example, all the satellites are in the same plane. That is Pluto's equatorial plane, as a matter of fact. And the amount of angular momentum in the system, which is, it's kind of a fancy word, but it's a very important quantity in science, tells us that either somehow the material in Charon was ejected in a giant impact and really couldn't have occurred. You couldn't get this angular momentum with a capture. So it doesn't look like there's a good competitor to the giant impact theory. New Horizons is going to help shed light on that. It already has, for example, determining that there are no other satellites in crazy orbits aside from the equatorial plane. It's going to tell us a lot about the geological histories of Pluto and Charon. It lets us count craters on their surfaces, and eventually we'll be able to age date them. It looks from a first very preliminary analysis like the oldest places on Charon are many billions of years old, which is consistent with the giant impact because there were many more impact progenitors back then than there are now. So far, a lot of circumstantial evidence to the crime, but we haven't actually got the fingerprints to seal the case. And if we can't do it with New Horizons data, that'll probably be an objective for the orbiter.
Well, considering how big Charon is, it must have been quite an event when that impact happened.
Well, absolutely. And the work that's been done has been led by Robin Canup. Others have worked on it as well, including Bill McKinnon, for example, on our science team. And the progenitors that they require in the computer modeling are things at least the size of Charon and more likely about the size of Pluto. So it was a big bang for sure.
Thanks.
All right, Alice, I know you had to leave around the end of the hour, so I know you've got to run. So we really appreciate you joining us and telling us your crazy stories of the July 4th event, but also all of the wonderful sort of events from New Horizons. And we really look forward to all of the future flybys and all of this updates of all this data that's coming down. It's been wonderful, and thank you so much for keeping the spacecraft on course and operating so well.
Okay, thank you, Fraser.
Thanks for joining us. Now, Alan, you're going to stick around. We may take a couple more questions about Pluto New Horizons, and then you may join us and talk about some stuff that has nothing to do with Pluto New Horizons, instead about Elon Musk trying to nuke Mars. So,
Love to.
all right. Let's. I saw Emily. You had a question?
Yeah, Alan, I'm noticing there's actually more images showing up on the Raw Images website as we speak, which is pretty exciting.
That's because there's one person who's putting them there. So it takes me time.
Well, thanks very much to the one person who's got the finger on the button back there. One question that I have that I'm hoping you can explain to people is, why do there appear to be a lot of pictures that look pretty much the same, like New Horizons was snapping the shutter multiple times? How does that help you out, and how is it so valuable to get so many similar images on the ground?
Well, there are images that are almost the same, and we do that for a couple of reasons. One is that some of these are from the stereo data set, so they're taken not very far apart in time. Secondly, there's a bug in the operating system of our command and data handling computer that every once in a while, every year or two, causes that computer to reset. And if it does, it takes about 6 minutes for it to come back online. So for all the important high-resolution imaging, like the stuff that's showing up now, every time we'd make an image, we'd always make another image at least 6 minutes apart in time, so that if lightning were to strike, we've got the data one way or the other. Having two sets of the data just allows us to co-add things or compare things for temporal changes, or do poor man's stereography if they're too close. So there are lots of benefits to doing it this way. But over time, as you see things unfold over weeks, not just days, of imagery and spectra being downlinked, you're going to see a very great diversity of data. And for the secondary and tertiary priority stuff, a lot less repetition, because there we judged that it was more important to get variety than to back it up. And most of the backups were for Group 1 data, which is coming to the ground first.
So this question comes from Mohammed Iftikhar Yidzani. He's from Pakistan. He'd like to know how difficult it is to guide, navigate, and control New Horizons from so many million miles away. So can you talk just a bit about, like, what's it like to try and tell New Horizons to maybe do new things at such great distances?
Well, it's all remote control with long round-trip light times. That's part of the challenge. So you have to make your moves very carefully. You certainly don't want to make a move that puts you in a bad spot, because it takes a long time to recover from that. Like the July 4th event, where we did it to ourselves. Actually, the techniques that we use for the most part in commanding New Horizons and guiding it are techniques that were developed over decades by our predecessors. We stand on the shoulders of giants is kind of a hackneyed phrase, but it's true. In the 60s and 70s and 80s, they developed techniques for flying to the planets, even as far away as Neptune, and successfully conducting reconnaissance flybys, and we built on those. So largely we tried to only deviate from well-proven processes and techniques where we had to get the job done at Pluto. But most of what we did was just good practice that had already been developed previously. The round-trip light times that we had were not very different from Voyager, for example. One of the things we did have to contend with is that because Pluto's a small planet and very far away and hasn't completed a full orbit, our knowledge of Pluto's position was considerably uncertain. So on approach, we had to do our own navigation and send imagery back to the Earth that we could use to home in. We actually made 3 engine maneuvers as a result of that to hit the aim point, which we did very, very well. I think New Horizons has about the best team of navigators and mission designers a PI could ever hope for. I know that there are other groups out there that are doing spectacular missions like Dawn and like Messenger and Cassini and so forth, but the group of people that APL put in place for New Horizons, they made it all look easy, and I know it wasn't. And they hit the aim point at Jupiter and at Pluto, first try, right down the middle of the pipe both times. I couldn't be happier.
Now, you're a guy who likes to consider the names of things, Alan, and so this question comes from Don Grenier. Do you have a more catchy name for 2014 MU69, which I guess is the next targeted object?
Well, the only other thing that we call it is PT1, Potential Target 1. But it will get a name before the flyby. We will find a process to do that. It won't be Alan's name for it, or it may not even be the science team's name for it. But working with NASA, we'll decide on a process and get it named. And by the time the spacecraft gets there, I imagine that'll be official and very, very well known.
Okay, so you're telling me that there is no internal name that you're just not telling us? No?
We don't even call it Fred. No.
No.
We call it MU69 or PT1.
PT1. Okay.
Sorry,
right.
It's too boring.
No,
the
no,
headline writers will thank you for picking a shorter name eventually.
Okay. Thanks, Nicole.
All right, I got a bunch more questions. Let's see. So this one comes from Sylvan Westby. How much delta V is left in New Horizon, and is there potential for visiting another body after P1?
Yeah, there's 36 kilograms or so. That's the number that's good to plus or minus a kilogram on board that we can use for every purpose, from pointing the spacecraft to changing its course. And every kilogram of fuel buys us about 5 meters per second. So you can multiply that out. 36 times 5 is a number like 180 meters per second. Now, we can't use it all for course corrections to motorboat around the Kuiper Belt, because we have to also use fuel for flybys, for flyby rehearsals, for cruise science, for pointing at the Earth to transmit data to the ground. And our current plan for PT1 is that from the studies that we've done so far, after we do the cruise science and along the way, and the flyby itself, and shipping the data home, we should have something between 5 and 15 kilos left, probably the lower end of that range. Now, we only need about 1 kilogram to fly a Voyager-like interstellar mission. So we can look around for another KBO to fly by. But the mathematical models tell us that we're unlikely to find one, because that's less fuel than we had for PT1, and we're further out where things are more dilute. They're further between objects, and those two things conspire together to just tell you it's a bit of a long shot. So we're going to look, and I can guarantee you that if there's a second target out there that we can reach, I'm going to work real hard to get us there. But we haven't begun that search yet. I think first we want to get the first extended mission squared away with NASA, and then think about the second, not in the other order.
So this comes from Laurel Kornfeld. Is there any chance of finding any moons in some of the data?
Oh, for Pluto, absolutely. I think, and we're going to be doing that, in fact. There are many images, all of which will be looked at. One of the things that we decided a long time ago is that we will not edit images to just send the primary target back to the ground. We'll send everything to the ground, even all the blank pixels, because you never know. You know, in the case of Voyager, there were satellites discovered 1 and even 2 decades later by people who developed new data analysis techniques. And then they wanted to go back when they found it once and see what other images they could find it in to learn more about it and its orbit. So we're sending everything to the ground. We're going to look at everything very hard for that reason and for other reasons. And I guarantee you we'll raise our hand as soon as we find something.
So this pool could last for decades on the number of moons discovered.
Oh, it could. I don't think that. I mean, there'll come a point of diminishing returns that will not be decades off, where we've scoured the data for anything obvious, even not so obvious, because we look very hard and we have very sophisticated techniques. But it's always possible, just like with Voyager, somebody smart 5, 10, 15 years later finds a way to do it better and makes a discovery.
All right, so we've got about 20 minutes left, and we have to catch up on all of the space-related activities that happen over the entire summer. So I think we should get cracking in on some of that stuff as well. Actually, we're going to do just the big stuff that's happening in the last little while. So I know, Alan, you're going to have opinions on this, so we'll treat you like a regular contributor now, and you can tell us what you think about some of this stuff as well. So first, I think we're going to switch to it being This Week in Musk. And Morgan, there are plans. Elon Musk apparently wants to destroy Mars or bomb Mars or nuke Mars. What's going on?
Yeah, so Elon's long-term vision for Mars is a planet like Earth that has human settlers on it, that has its sort of own thriving economy, so on and so forth. And to have sort of the best settlement that you could have, you probably want to be able to walk around on the surface without a big bulky spacesuit. One day you might even want to be able to take off your sort of space scuba mask and breathe in that nice fresh Martian air, and basically turn what's right now sort of a dead, lifeless planet, as far as we can tell, into one that's capable of more easily sustaining human life. And last night on Stephen Colbert's new show, he announced that he has a new plan to do this, and it's to nuke the North and the South Pole of Mars, presumably repeatedly. Basically, in order to terraform a planet like Mars, what you need to do is thicken up its atmosphere. And there's the slow way and the fast way of doing that. And the slow way is to sort of go under the surface, scoop up that nice iron-rich Martian soil, start doing chemical reactions to create rocket fuel and electricity and water and all of these good things, and then pollute. And as human beings, we're excellent polluters, and over time we would fog up the atmosphere enough that we might be able to affect actually useful climate change on Mars. But we also have these huge stores of volatile material on the poles in the form of the ice caps. Most of this is carbon dioxide ice, which happens to be a very good greenhouse gas. And so his idea is to drop thermonuclear weapons on the poles of Mars, vaporize a lot of that ice, turn it into gas, and then use that gas basically as a blanket to heat up Mars. Now, needless to say, there are more problems with this notion than we really need to go into right now. Of course, number one being that you're trading not being able to breathe the air for radiation everywhere, but also subtler problems that scientists in the last 24 hours or so have pushed back against and said, look, this is not the right way to go about this goal, even if that sort of is a long-term desire that we might have.
See,
Okay,
that's why Colbert suggested Musk might be a supervillain.
We've actually been doing a series on the Guide to Space videos. We covered terraforming Mars, terraforming Venus, terraforming the Moon. People wanted me to figure out how to terraform Jupiter, so I did that. And then the Sun. So I just did a video on how we would terraform the Sun. And next week is how we would terraform a black hole, which is just ever more ridiculous. The fact that we can't even send human beings to the surface of Mars yet, I think, puts that nuking process down the road a bit.
Yeah, the best point that I've seen made sort of in the last 12 hours is that, given an Earth-like environment here on Earth, we can't even make sort of subtle adjustments to it in order to make it the sort of, place that we'd like to live. What makes us think that we could take a planet so unhospitable to life that we could magically, with a few nuclear weapons, turn it into a place that would be, even vaguely good for us to live on?
Alan, I know you are a fan of robotic space exploration, and how do you feel about sort of the human civilization of other bodies in the solar system? The Moon, the Mars, which would you pick?
Well, first of all, Fraser, I'm a fan of human and robotic exploration, and I'm a big fan of Elon Musk's as well. He is a genius, and he has very good motivations in wanting to colonize Mars, because he wants us to have, a second chance, a second place if there's ever some catastrophe that affects the Earth, such as a bad impact. So I think that Elon is really leading the thinking in the world on something like this, and I think that the conversation is a good one to have. He knows very well that before we terraform Mars, we need to first send human beings there, and to the best of my knowledge, he intends to be first to do it. and my hat's off to him for that. I'd like to see us return to the moon as well and have bases there just like we do in Antarctica. I think that would be very, very profitable scientifically. The moon has a lot to teach us. It has a lot to teach us about how to mine not just the moon but eventually asteroids, how to live on other worlds, and I think it has a tremendous inspirational dimension as well. You know, one of the things that I'm most satisfied with about New Horizons is how many people it inspired for exploration. And I just can't imagine the power of having a moon base, particularly a base on the near side, that you could look up at and see against the lunar night side as a little glowing ember, a light, that parents could point for their children and say, humans are living there. That must be a future which is very inspirational, and I hope that I live to see it. And I'd like to see us all over the solar system. I share the kind of vision that any of you who saw the viral video Wanderers last year saw, of humans across the solar system exploring and doing other things, building economies, as Elon says. I think that would be a wonderful future for us.
It looks like Emily is processing images in real time as we go here. So Emily, I don't know, are you ready to show us what you got?
I was just trolling the website, and I noticed that all of a sudden this huge pile of new Pluto images appeared that make a glorious mosaic of the northern half of the disk. Alan, can you tell me, is the southern half of this disk also still on the spacecraft?
Well, it's hard to tell what you're talking about, Emily, but the entire close approach hemisphere is now blanketed with images that are on the spacecraft.
Here.
And the best ones that are on the ground are 400 meters per pixel. And they cover about maybe 25 or 30% of the disk. There will be imagery coming down at 250 meters a pixel, about 125, and at about 80 meters per pixel in the future.
I'm just looking at all of this terrain up here and thinking that there's really subtle albedo variations, and I just cannot wait to see what the color data tells us about what's happening all up in here.
Well, we were talking about that on the science team because we're going to have the stereo for topography, we're going to have the compositional maps, the color maps, and higher resolution. So we're going to have a lot more firepower to put on this than we do now. Right now, I think we're just full of questions. I just can't get over how complex Pluto is. I just can't get over this.
It's pretty great. So congratulations again. It's really
exciting,
awesome.
But it's bewildering to deal with. I don't think Triton set our expectations correctly at all.
Well, so Emily, you had a moon there too, so maybe we can come back around and take a look at that as well later on.
Oh yeah, I was just looking at some images of Hydra. This is way zoomed in, but it's similar to ones that have been downlinked before, but because of the lower compression, you can see impact craters here that weren't really visible before, so that's pretty cool too.
Does it have some kind of duck neck structure as well? I don't know.
I have to ask Alan about that.
It looks a bit ducky to me.
Yeah.
Yeah, Emily and I were calling it the catcher's mitt or the cooking mitt.
It looks like a little horse.
It's a pony.
It's like an animal cracker.
It does.
Undefined animal shape.
It's a Rorschach test.
I like that.
Well, so let's move on with some of the other big events that happened. Like, for example, further confirmation of the Big Bang. Brian, cosmic neutrino background radiation detected.
Yeah, this is a fascinating one because we're familiar with the cosmic microwave background, which is kind of the thermal remnant, and that's from a period when the universe was about 380,000 years old. And the neutrino background was just when particles were being put together at about 1 second. And because neutrinos don't interact strongly with anything, they can go right through stuff. So in principle, we should be able to detect it. The problem is the neutrinos, the kind of primordial neutrinos, are far too cold. The estimated temperature is around 2 Kelvin. So we have no way of detecting them directly. But the interesting thing is that even though these neutrinos don't interact strongly with material, they do interact a little bit with material. And so what they can do is by interacting with the energy and the radiation from the cosmic microwave background, they can shift and distort the background patterns a little bit. So if you look at the levels of clumping, within the cosmic microwave background, or the fluctuations within it, you can see this shift. And so just recently, this shift has been measured. And what's interesting is you can compare the shift to different models. And what they did, the team did this and compared the shift to a model in which you have 1, 3, or 5 neutrinos. And what they found matched perfectly with 3 neutrinos. So it's an indirect detection of this microwave background, and it's a confirmation of 3 neutrinos.
So is that another just independent piece of evidence for the Big Bang?
Yes. Yeah, because it traces back into the earliest moments, and so the thing of baryogenesis, for example, when particles, the primordial constituents of matter are being made, that's what you can detect. And apparently from the Planck data, when we get the full polarization data released, I think in December or January, we should be able to pin down what the temperature of that neutrino background is by the shift. The level of shift in more detail will actually determine what the background is. So we can actually test whether or not it is at, I think, 1.98 Kelvin, which is the calculated temperature.
Now you said that this... Oh, go ahead, Morgan.
Yeah, so what does it mean, Brian, for a neutrino to have a temperature?
It's amount of the energy level. So that basically when the neutrinos were first produced, they were produced with high energy. And so, in the same way that you would have particle physics, you've got neutrinos being produced. But because of the expansion of the universe, they lose energy. In the same way that photons can redshift, neutrinos can lose energy. And so you can ascribe a temperature distribution to this.
Brian, can I ask a question?
Sure.
Why is this discovered only now? In other words, was it development of new techniques to analyze the data, or was the idea that you could even do this particular kind of data analysis only recently discovered? Or why now, since the data sets have been around a while?
I think because as we're getting more data sets and better analysis tools, you finally reached a sweet point. So because it's a small fluctuation within the power spectrum. So when you look, what are traditionally the peaks of where things would clump, it's a small shift of that. And so this was from the Planck data, the latest Planck data, which was, the 9 Skies survey.
But you're saying that these neutrinos were released earlier than the cosmic microwave background radiation, right? Which is 300 and something thousand years after the Big Bang. So does this give us a technique to perhaps probe closer to the Big Bang?
Yes. In fact, if we can measure the thermal temperature of the neutrinos, we can confirm whether the hot Big Bang model that everything seems to be pointing towards is there, and it's an independent confirmation of that.
So this is 1 second after the Big Bang?
This is 1 second after the Big Bang, yeah.
It's 12 orders of magnitude earlier than 100,000 years.
Yes.
Yeah. Does it give us another independent way to maybe look at the presence of inflation, which you rained on our inflation parade all last year? So does this bring it back to us?
I'm not sure. It certainly will give us a better indication of baryogenesis in those early moments. Inflation was even earlier than that. I think, and I'm speculating, but if we have the thermal temperature, we would then know basically the size of the observable universe at 1 second. And so that would, in fact, at least point towards the direction of an earlier inflationary period. So we would know, how big the universe is at 1 second. If it's as big as we think it is, then that would point to the idea of inflation.
So Planck taketh away and Planck giveth.
Planck may giveth, yes.
Yeah. Okay, so we've got about 6 minutes left and before the end of the time, and I know everyone's time is super busy, so I'm going to give sort of just like 1 minute for the rest of everyone to quickly present their story, and I apologize in advance. I blame Pluto. So, David, there's an eclipse coming up.
Yes, Eclipse Season 2 of 2 for 2015 is starting this weekend. It's a partial solar eclipse, and it's kind of really not a huge event because it's only going to be like 40% partial for Antarctica in South Africa. So most of the pictures were probably... SLU, I know, is going to be broadcasting it live. It's early Sunday morning for U.S. East Coast is when it occurs, so it's going to be sunrise for South Africa. However, that sets us up for a total lunar eclipse on the night of September 27th, 28th. That will be a big event because it is a perigee moon. It is the last lunar eclipse of the ongoing tetrad of 4 lunar eclipses, and it's going to be visible for Europe, North America, South America. It's going to be on the evening here in North America, so it's going to be a very, it's not like 4 in the morning or something like that. So it's going to be a lot of people are in the eclipse zone for this total lunar eclipse, and I fully expect the super blood moon like woo to come back around again like it always does. This one, like I said, is the perigee closest full moon of the year. I like to call it the Proxygean moon, but I know the internet calls it the super moon, so we're kind of stuck with that meme right now. So it's going to be a big event for and lunar eclipses are always fun to watch.
Yeah, for me on the West Coast, the moon will be rising and then just start to go eclipse shortly after it starts to rise. It couldn't be more perfect. I won't have to get up in the middle of the night. This is awesome.
This is the last well-placed total lunar eclipse till 2019. Next year there's a few penumbrals, and the next year the big eclipse is going to be the total solar eclipse for Southeast Asia in the spring. So that's going to be the next big season coming around.
Fantastic. Nicole, the GBT adds the SETI project. What?
Yes. Hi, everybody. So I survived my summer hiatus from everything. And the one story that made me squee the most when I opened up my inbox and saw this was that the Green Bank Telescope in West Virginia, one of my favorite telescopes, one of my favorite places in the world, probably because I spent so much time there as a grad student, has added a contract to work with a SETI project, so Search for Extraterrestrial Intelligence, with the Breakthrough Prize Foundation. It's called Breakthrough Listen, which makes me cringe because, you know, radio, we don't listen, it's light, but whatever. But that's really great news for the GBT since they are looking for help with operating funds. As far as I know, I think it helps with the operating funds. So they're going to be starting early next year. About 20% of the observing time for the telescope will be dedicated towards looking for signs of intelligent life, which is awesome because somebody recently asked me, I think it was at DragonCon, so when do you think we're going to find intelligent life? And my answer was, but you know, this is one more way of helping the search. That's all I got.
That's awesome. I look forward to communication with our alien overlords. Ramin, why don't we talk about the Celeste telescope?
Sure. So Celeste is actually so it's not a telescope but a model. It's sort of a they're describing it as a way to catalog the whole universe. Which is there's you know, some truth to that, I guess. They're starting with the Sloan Digital Sky Survey, where people have observed millions of galaxies, as well as many stars and quasars. And what they're doing is they're basically trying to make the most of this gigantic data set. It's it's all data on Earth, so it's a lot easier than, say, New Horizons, but it's like 10,000 times as much data. So it's like a huge amount of data. Photometric data, so images of all these different objects. And so what they're doing is they're putting all of this imaging together and see what they can learn. So it's basically making a combined data set using both statistics and all of this survey data that will be a huge resource for astronomers for many years. And there's really these statistics and computing experts in the astronomical field who are doing it. So I think this is going to be the beginning of something that's very useful for many years.
Awesome. Okay, well, I'm going to wrap it up right here. I'm going to give everyone a chance here to let people know more about them and where they can find out more. So, Alan, we'll start with you. Where can people find out more about what you're working on and the projects that you're associated with?
Well, since we talked primarily about New Horizons, you can go to nasa.gov and find the New Horizons NASA site, or you can go to the Johns Hopkins Applied Physics Lab, jhupapl.edu, and /Pluto or /New Horizons, and find out a lot more. You can also just Google it up because there's so many resources that are out there. For myself, I'm on social media. You can find me on Twitter at Alan Stern, and you can find me on Facebook, same place. Thanks.
Fantastic. Brian, where do we find out more?
You can find me on my website, What's One Universe at a Time. It's briankoberlein.com, or on Twitter at Brian Koberlein, or Facebook at Brian Koberlein. And you should all support my Patreon, because if I don't say that, then Fraser will.
Nice. David.
Astro Guys with the Z, and I'm still putting up self-published sci-fi. I'm offering free chapters every week. Every Friday, there's a new chapter up for a new story right now. And I was active this summer. I picked up a few new gigs. I've been writing Course for Universe Today, Listosaur, and I've been writing for Sin. I think I just started when we went on hiatus. And Sky and Telescope Online as well. I've been writing for them.
Recently updated pictures of Pluto. Where can we find out more?
Yeah, you can find me at the Planetary Society at planetary.org, and also on Twitter at Lakdawalla. That's where most of my output is, but I also write for Sky and Telescope magazine from time to time.
Oh, she just cut off. I was about to pull a Brian Koberlein on her, but I'll have to come back.
Ooh.
Oh,
No.
Wait.
And I'm working on a...
She's working on a book about curiosity.
Is she working on a book? Is she working on a movie? Is it an interpretive dance? What is she working on? Emily, what is it that you're working on? A book about curiosity, maybe?
A book about curiosity, yes.
And let's say that a person is really enthusiastic about space and really wants to find some large group of like-minded people, a society perhaps, that they can join. How can they do this?
They should just go to planetary.org and click the great big join button and join us in supporting space research and exploration all over the world.
Awesome. Everybody do that. We'll wait. Morgan, where do we find out more?
Yeah, you can always find me on Twitter at Morgan Rehnberg. And if you're in the Denver metropolitan area tonight, come out to Fisk Planetarium at 7 p.m. to see my latest show. It's called Go Big or Go Home, Astronomy and the Dawn of Big Science.
When you say show, is this like a planetarium show? Are you speaking? What's going on?
It is both a planetarium show and I'm speaking. You might see some of my beautiful posters behind me here. We do a great show every month where we explore a new area where science interacts with society and then have a big conversation about it with the audience.
That sounds awesome. Nicole, where do we find out more?
Hi, everybody. I'm in New Hampshire now. I am Dr. Nicole Gugliucci. I'm now an assistant professor of physics and astronomy. I don't think astronomy is part of my tag, but I add it. At a small liberal arts college here in New Hampshire. And you can see me on Twitter at Noisy Astronomer. Now that I'm back from my life vacation, I will be posting more and fixing my website. Yes, I know it's broken. I will fix it this weekend.
No one said it. There was a problem here, Nicole.
People emailing me like,
oh, okay.
Hey, crap's broken. So.
Ramin, where do people find out more?
You can find me on Twitter at Ramin Skibba, and you can see my blog where I write a bunch of articles about various political and scientific topics. It's Science Political. The URL is raminskibba.net. And I'm actually, as of next week, moving north to Santa Cruz for the Science Communication Program. So watch for, I'll post articles on raminskibba.net when I write them there.
Fantastic. Okay, once again, Fraser Cain, publisher of Universe Today, and if you're interested, we're going to be doing a live rehearsal of the next batch of videos that we're doing. So we've got the next 8 videos that we're going to be doing, and we rehearse this live on Periscope. So if you're not already following me on Periscope, go ahead and follow me. We're going to probably start that up in the next couple of hours. You'll get a notification on your phone because Periscope does a really good job of telling you when a thing that you really enjoy that's live broadcasting is happening live, unlike some other technology that we're not going to mention. But yeah, so if you want to do that, follow me on Periscope, and then we'll start that up, and it'll take us about an hour to kind of go through all of the episodes. We'll answer questions. We'll be silly, and we'll do that shortly. So if you haven't already, follow me on Periscope. I'm F. Cain, I think. Cool. Well, hey, thanks everybody. What a wonderful return to the Weekly Space Hangout with our special guests. Alan, as always, it's a pleasure to have you join us, and we cannot wait for all of this data to come in and the new discoveries, and for you to tell us all the big surprises that are coming shortly.
Thanks for having Alice and I on, Fraser. It was a blast.
All right. Well, thanks everyone. Thanks to all of the viewers watching this.
I missed you guys.
Okay. A reminder to go to the WSH Crew community on Google+. These are, of course, the producers of this show, the ones who organize the stories. They are now organizing the guests. You couldn't fall into a better group of people. So thank you so much. They've actually created their own website now, and it's just phenomenal being in partnership with this group of people. So we really appreciate everything. I think you can go to bit.ly/WSH Crew is a quick link to go to the community, and it's great. All right, well, we're going to wrap this up. So thanks, everyone, and we'll see you all in a week. See you later.
Bye, all.
Bye, everyone.